Let's now welcome Dr. Marijan from Imperial College London. He will be talking about manipulating the Bloch points in Helimagnetic nanostructures. Welcome.
Thank you very much. Could just somebody confirm that you can hear me and you can see my slides?
Yes.
Great. Well, thank you very much. Good morning, good afternoon, good evening, depending on where you are around the world. I'm Marijan, and I will give us a summary of how we could manipulate Bloch points in Helimagnetic nanostructures. Earlier today, my colleague Martin Lang showed how we could have multiple Bloch points in Helimagnetic nanostructures, and now I'm going to have a look at, actually give a quick overview of possible techniques and methods how we can manipulate them. So I would first like to start with a thought experiment that led us to try to stabilize Bloch points in these kind of structures. So if we have a magnetic vortex in a disk, magnetic vortex can have 4 possible states, because we can have 2 different chiralities, let's say clockwise and counterclockwise, and we can have 2 different core orientations. Now, if we put on top of each other 2 vortices that have the same chirality, let's say in this case clockwise, but have different core orientations, we end up with the magnetization field that is continuous everywhere, except in the point in the middle. And that point is a Bloch point. Now, if we don't have DMI in this system, Bloch points are energetically very expensive, so the system will do everything it can to lower its energy and expel the Bloch point. But by adding DMI to the system, more precisely by adding DMI of the opposite sign in the top and the bottom layer, we can restrict the orientation chirality relationship and keep the Bloch point inside. And to study our hypothesis, we started with a very simple model, which is, so our energy density contains only isotropic exchange, DMI in its bulk form, and the demagnetization field. We assume the isotropic material, so there is no magnetic crystalline isotropy. In the beginning, I will just show simple dynamics, which is a well-known LG equation. We simulate a full 3D model, which means we don't make any assumptions about translation invariance of magnetization in the Z direction. And for simulations that I'm going to show you today, we use 2 different simulation tools that we developed. One is called UberMag and another one is called FinMag, and you can have a look at these links if you're interested in more details. So let's first look at the stability. So to find more about what the Bloch point is and when it's created, we simulate a disk of 150 nanometers that consists of 2 layers. You can see in these 2 layers that the sign of D is opposite. So the absolute value is the same, but the sign is different. We fix the thickness of the bottom layer to be 20 nanometers, and then we vary the thickness of the top layer. Material is iron germanium with these material parameters. And what we find is that for the thicknesses of the top layer, it is energetically cheaper for the top layer to follow the magnetization of the bottom layer and not to form the Bloch point. However, if the thickness of the top layer is larger than approximately 8 or 9 nanometers, then it is energetically cheaper for the system to introduce the Bloch point in the middle rather than for the entire top layer to follow the magnetization of the bottom layer. And here in these cross section, so to say, you can see that for the small thicknesses of the top layer, basically the magnetization in the top layer follows the magnetization in the bottom layer, whereas if the top layer is thick enough, in this case larger than 9 nanometers, then the Bloch point is introduced so that both vortices have the same chirality, but they have the opposite orientation. Then we try to look at the hysteretic behavior, and when we found that the system undergoes hysteretic behavior by varying an external magnetic field, and we found that we can have 2 different types of Bloch points that could be head-to-head or tail-to-tail. So this is the first example of how we could manipulate Bloch points by applying an out-of-plane magnetic field and switch the type of Bloch point from head to head to tail. Then we try to look at different geometries. So far, I only show you the Bloch points in a disk, but somebody could ask, okay, couldn't we have it in different types of geometries? So these are top views. We can have them in nanodisk, nanosquares, nanostrips, something that I'm going to show a little bit more details later. And then also here's some funny shapes such as nano asteroids and nano hearts. So basically we can have Bloch points in a very wide variety of geometries. Now, so far in our work, we demonstrated that Bloch point is an equilibrium state. So it is there, it's stable. We found that there are two different Bloch point types, head to head and tail to tail, and we found that Bloch points emerge in a wide range of thin film geometries. But now, is there anything interesting we can do with Bloch points? So can we change their type? Can we move them around? Can we nucleate them on demand? And could we maybe have multiple Bloch points in the sample? Multiple Bloch points, my colleague Martin showed that earlier today. So I will focus on how can we manipulate them using external magnetic fields or spin polarized currents. So first, if we look at the geometry, the disk geometry I showed earlier, but now we have a thickness of the top layer 10 nanometers, and we apply a field pulse that looks something like this, we can see that we can find in this phase diagram, we can find the values of an external field as well as the pulse durations where we can achieve the switch and where we can't. So here is an example of if we look at the cross section as I showed here, that if either the external magnetic field or the pulse duration are not long or strong enough, then we cannot change the orientation of the bottom layer. However, if we take parameters from this green region here, then we can actually change the orientation of the bottom layer. And after the relaxation, we can see that we can switch from the head to head to tail Bloch point. Now, slightly different geometry. We have a nanostrip, 450 nanometers long, 90 nanometers wide. Again, 20 nanometer, bottom layer 10 nanometer. Top layer, as usual, material is iron germanium. And now we applied an external magnetic field in plane. In this case, it's sort of in the y direction. We simulate dynamics, and we calculated the coordinates of the Bloch point by tracking the topological charge in the top layer. And we can see as the time progresses, our Bloch point moves. And by plotting the distance as a function of time for different external magnetic fields, we can see that the Bloch point moves in the positive x direction, or in other words, perpendicular to the magnetic field. And here is the first degree polynomial interpolation to get the velocities. And you can see the velocities are similar to those of skyrmions. Now, I'll quickly show other concepts, such as using current pulses to switch. Similar story, but now instead of an external magnetic field, we use spin polarized currents. And again, we can find regions where either the current density is strong enough or the pulse duration is long enough so that we can make a switch. Here, the spin polarized current is polarized in the negative z direction. Here, very similar. One thing that is interesting here that we haven't seen with an external magnetic field, and unfortunately I don't have enough time to focus on that, is that now, apart from the Bloch point only moving in the positive x direction, the Bloch point also moves away from the axis, which is something we see similar in skyrmions. Here, just a small reminder from that my colleague Martin showed earlier today, that we can also have multiple Bloch points in the sample. So here we can see one Bloch point and two Bloch points, and there's this transition region in between. So not only that they're stable, we can manipulate them using fields and currents, we can also have multiple Bloch points. And finally, I want to show how we could maybe nucleate Bloch points on demand. So here is a region where we're going to apply an external magnetic field, in this case in the negative Z direction. Again, it is a pulse. And we start with a single Bloch point in the sample. When we apply the field in this region here, we kind of cut off some, we kind of divide samples into different, into regions. And then in the second region, another Bloch point emerges. After turning off the field and relaxing the system, we can see that we have two Bloch points with this anti-vortex region in between. And the cross-section looks like this. I will quickly summarize. So far we've found a stable Bloch point at the boundary of between layers or grains of different chirality. We found that Bloch points not only emerge in the nanodisks, they also emerge in in various different geometries. Bloch points can be manipulated using external magnetic fields and spin polarized currents. In particular, we found that we can switch Bloch points type, we can move them in an arbitrary direction, and we can nucleate them on demand. And not only that, we can also have multiple stable Bloch points in the sample. This is my email address. If I don't manage to answer any of your questions or you're interested in more details, please feel free to email me. And finally, I would just like to acknowledge our collaborators as well as the funding. Thank you very much.
Thank you for the nice talk, Marijan. Now is the Q&A time. I see Jose, you have questions. So,
hi, Marijan. Thank you for the nice talk. I would like to ask you about the way you tracked the Bloch point, because it's the first time I see this approach. I mean, the usual approach to track the Bloch point is to evaluate the isosurfaces that have value 0 of every of the components of the magnetization, mx equals 0, my equals 0, and mz equals 0, and the intersection is typically the Bloch point. So this is the first time I see this approach.
So
my concern is, why do you use the 2D topological charge when the Bloch point is a 3D structure?
Yes, so we are tracking the Bloch point not by tracking the Bloch point itself. We are tracking the Bloch point by looking at the vortex core that is in the top layer. Okay. So we're basically these formulas here are the same formulas you can see in many papers to track fermions. So by computing the topological charge in this 2D layer here, can you see my cursor? Yeah, so by computing the topological charge in the top layer, basically we're tracking the vortex, and by tracking the vortex, we also track the Bloch point, which is right below it.
Okay, so you track the vortex on the surface?
Yes, yes.
Okay, thank you very much.
Yeah. There is also, just to mention, there is also a way to compute the topological charge of Bloch points. I don't know if Martin showed that earlier today, but feel free to get in touch and then we can share that with you.
I have one following question: that is there a way to fabricate this type of sample with the same material but with different D values on top and the bottom layers?
Yes and no. So the thing is, as I said, we started with a thought experiment and we've been looking at how we could maybe fabricate this. So one way is when we grow materials, you use an epitaxial growth, we see grains of different chirality. And one way would be to etch the samples in such a way that we capture those boundaries. However, there is another method where by changing the doping of certain materials during the epitaxial growth, we can also change the sign of the DMI. So we could, let's say, grow the material with a positive DMI, and then during the epitaxial growth, we change the doping, and then we continue growing a layer with negative DMI. But so far we haven't fabricated anything like this.
I see. Thank you. Any questions? So if there's no question, let's thank Marijan again and then move to the next speaker.
So next speaker is Daniel Guillermo ACTIS from Instituto de Física La Plata, Argentina. So Daniel.
I'll be now sharing my screen. Thank you very much. See, very well. And thanks for the opportunity to participate in this peculiar conference around the globe. I'm Daniel Guillermo ACTIS, physics doctoral student, and I'm going to talk to you about electromagnetic SAR determination and some short results we obtained measuring magnetite nanoflowers in a melanoma tumor and inside an Agarosa ferrohead. I'm speaking to you right now from the city of La Plata in South America, some 60 kilometers southeast from our Argentinian capital of Buenos Aires. And this right here is the Instituto de Física de La Plata, where our labs and offices are located. And although I'm presently at home according to COVID-19 protocol, I'm optimistic that soon enough we'll be able to do the totality of our scientific practice there again. Our work group is the group of magnetism and magnetic materials, or G3M, where we dedicate ourselves to the study and design of new magnetic materials, magnetic characterization, nanomagnetism in general, and in particular, biomedical applications of magnetic materials. One of these such applications is the therapy of magnetic hyperthermia, where the goal is the localized heating and subsequent death of tumor tissue. The heating efficiency of the nanoparticles is quantified by the specific absorption rate. That is to say, the amount of power that the nanoparticles absorb from the field per unit mass, and which then they release to their surroundings as heat. SAR is affected by several factors. On the one hand, we have the nanoparticles' properties, such as magnetic moment and anisotropy energy, but we also have the viscosity of the medium to take into account, and the interactions between particles and between the particles and the medium. And also, of course, the AC field characteristics, that is to say, frequency and amplitude of the radio frequency field. Traditionally, SAR is measured by a calorimetric method, where the sample is loaded with nanoparticles and placed inside a solenoid, and its temperature probed with an optical probe. After turning on the RF field, we see a temperature increase with time, and its slope is used to quantify the SAR, taking into account the specific heat of the material and the NP concentration. This method has several limitations. On the one hand, the localized probe can lead to irrepresentative measurement in the case of an inhomogeneous sample. It's difficult to measure solid sample, and it takes extended time if the sample doesn't heat fast enough. And also we have to take into account the time it takes after turning off the field to cool down. Also, any heat losses the system may experience affect the SAR measurements. And the only information we obtain of the sample of the nanoparticles is this temperature increase versus time. So several authors have come up with an electromagnetic SAR technique via magnetic induction. Here the sample is placed inside the same field generating solenoid, but also inside a pickup coil, and another pickup coil lies in a position of equal field strength as the sample. Both pickup coils are oppositely connected, and there's an additional larger field coil outside the solenoid. Both electromotive forces are measured by a digital oscilloscope, and the physics behind the method is none other than Faraday's law. So we can obtain both magnetization and field versus time, integrating the respective electromotive forces. Having both those functions of time, we can construct the corresponding hysteresis loop, where we have magnetization versus field, and the area, the surface enclosed by this loop, is the work done by the magnetic field on the nanoparticles, which is the same energy they will be releasing as heat to their surroundings. From here, we can calculate the SAR simply as work times frequency. With this technique, we have here the Hüttinger radio frequency source. We have this range of frequency and this range of amplitude. And there are two typical loops results. At low field amplitude, the response to an AC field is a sinusoidal magnetization with a time delay corresponding to the relaxation time of the particles. The hysteresis loop in this case takes the form of an ellipse, but as the field amplitude increases, the magnetization is additionally distortion. We have still the time delay, but the signal is no longer sinusoidal. There are higher harmonics in play, and the resulting loop gets a little distortion as the magnetization approaches saturation. Having described the technique, we move to our system of choice. In 2018, Corral et al. Synthesized magnet and nanoflowers for magnetic hyperthermia studies. These nanoflowers of here 34 nanometers diameter are composed of smaller magnetite nanoparticles of 8 nanometers diameter, which are crystallographically aligned, forming the nanoflowers. They were done by a co-precipitation protocol. And they took these nanoflowers and they prepared two kinds of systems that would incorporate the particles, Agarosa gel and actual mice and melanoma tumors, which were injected in vivo and excised for this study ex vivo after 24 hours. They measured the SAR for both these systems calorimetrically and obtained repeatedly lower values for the tumor than for the ferrogel. In their words, dosage had to be increased to achieve the same temperature increment that was predicted studying the gel phantoms and the ferrofluids. Well, so they allowed us to work with one of these tumors and the Agarosa gel phantom, and we cut the tumor in 4 sections in order to fill the pickup coil volume. The one was closest to the mouse skin, and the others were below. T3 was sorely damaged during measurements, and after the electromagnetic SAR measurements, we were able to determine iron concentration for every measured sample by spectrophotometric determination. It's important to note that the ferrogel had an iron concentration of about 5 grams per liter, of the same order than the 7.7 of the T2, but T4 has almost 31 grams of iron per liter. This is a direct indicator of inhomogeneity of nanoflower distribution inside the tumor, that has to do when the nanoflowers were injected in the mouse. For the electromagnetic SAR measurements, these samples, we picked 3 frequency configurations, 98, 170, and 260 kilohertz, and 2 field amplitudes of 17.4 and 54 kiloampere meter. Well, as we can see, the ferrogel loops were consistently larger than both the tumor magnetization versus field loops, and the tumor portions between themselves were quite similar in every configuration. And moreover, at low field amplitude, the ferrogel shows a non-linear behavior, while the same nanoparticles in the tumor behave linearly. In regards to the SAR obtained from these loops, it's consistently higher for the ferrogel than for the both portions of tumor, and it increases with field amplitude and frequency, but that is well expected. According to the loops we have seen, the SAR is similar for both portions of the tumor and consistently lower than the SAR obtained from the ferrogel. So what can we conclude from this very simple result? Having seen the similar loops and SAR of both portions of tumor with very different iron concentrations, we confirm that at least global concentration of nanoparticles is not the main factor behind the SAR differences with the ferrogel. At the same time, the similarity between both tumor portions, it suggests a similar nanoparticle environment despite the increase in concentration. The qualitatively difference for the ferrogel at low field is also an indicator reminding us of the difference in environment the nanoparticles have in vitro, even in phantom systems such as the ferrogel, and in vivo in the actual tumor. In regards to the technique, to the electromagnetic technique, as far as we know, these are the first magnetic radiofrequency loops of nanoparticles inside the tumor, which is something in itself. And this technique allows us to measure the actual magnetization versus field loops of magnetic nanoparticles inside any kind of non-metallic medium. So we are accessing really the nanoparticles' instant response to the radiofrequency field. From there, we can obtain not only the SAR, but also the coercive field, the remanence, and the relaxation time of the particles from having the complete magnetization versus field loop. And we obtain all this information in situ, in the same medium where they will be applied, inside, in this case, inside a melanoma tumor. So, well, that being all, I thank you very much for your attention, and I'll be now open to your questions.
Thank you for your talk, and thank you for being on time. I didn't give you a warning. So we are now open for questions. Please raise your hand or write on the chat. So, I mean, your talk is quite changing gears from what we had so far, which is very, very interesting and one of the good things about this conference. So when you measure SAR, what are the intrinsic properties that you change? Is it the density or I guess or the conductivity? I don't think you gave like a formula for your quantity, right?
For the SAR, the specific absorption rate. From the electromagnetic technique, the formula is really just this one. We are measuring the electromagnetic work done on the system, on the sample, and for every loop, and then we multiply it by the frequency of the field. This is all the power, or the specific power that is entering the sample, which will be released as heat. No? Here in the magnetization, we have to take into account the concentration of the nanoparticles. Let's see the results. Here, the
magnetization. The concentration that changes.
Yeah. Yes, the concentration
should be inversely proportional to the concentration.
The SAR should be specific of concentration if there aren't additional interactions between the particles which affect the effective magnetic moment, for example, of the nanoparticles. For non-interacting nanoparticles in an ideal medium, the SAR should be concentration independent. But what happens when the concentration increases? Normally you have more agglomeration and more interaction between the nanoparticles. Here we are not seeing that, and that is interesting because both portions of the tumor have very different concentration and they respond the same way magnetically. So that's for future study, of course, but we are guessing that the agglomeration is done in clusters, and what is happening, what is changing with increasing concentration is the concentration of clusters, but not the shape and distribution of the cluster itself. Of course, this is only speculation. Further study is needed.
Great, thank you. We have some time for a question. If not, maybe the next speaker can start preparing.
Let's welcome next speaker, Jay Wang from University of South Carolina. He will be talking about heat induction behavior of injected superparamagnetic nanofluid interpreted by mass and heat transfer for clinic magnetic hyperthermia applications. Welcome.
So hopefully you can see my screen and hear my voice.
Yes.
Okay, Thank you for your introduction. So it is a great honor to present my research work here. So I'm Wang from University of South Carolina. The title of my research work is Heat Induction Behavior of Injected Superparamagnetic Nanofluid by Mass and Heat Transfer for Clinical Magnetic Hyperthermia Application. So I will present my research works from 4 parts: background and motivation, experiment simulation, results and discussion, and conclusion. So magnetic nanofluid hyperthermia has attracted a huge attention in cancer clinics because this method shows low side effects and high cancer cell differentiation and high treatment efficacy compared to other conventional chemotherapy and radiotherapy. And here is the general process of magnetic nanofluid hyperthermia. Like after injecting magnetic nanofluid to cancer tissues or target tissues, this target tissue will be heated by external AC magnetic fields. This heat comes from relaxation loss and hysteresis loss. So if this heating temperature can reach to 42 to 46 degrees Celsius, and then it can be used to kill cancer cells or target cancer cells with minimally damaging health tissues. So although magnetic nanofluid hyperthermia is very popular and is very appealing, there are still critical challenges in cancer clinics. The first one is the low AC magnetic heating efficiency. That means the low SLP or ILP, the specific loss power and the intrinsic loss power. And the second one is required high biocompatibility. And the third one is the inhomogeneous heating distribution. So many research works have been carried out to overcome these challenges, like by developing a new hyperthermia agent with high heating efficiency, or to design an advanced coating technology or surface modification. So however, the homogeneous heating distribution that is still regarded as a critical challenge because it is very difficult to precisely detect the temperature in cancer cells during magnetic nanofluid hyperthermia. So therefore, many research works have been done to investigate the heating distribution inside the biotissue to predict and analyze the distribution of heat induction temperature during magnetic nanofluid hyperthermia. But there are still several technical and theoretical limits in their proposed model and proposed methods. For example, like the temperature distribution they considered was just based on spherical shape of magnetic nanofluids. The magnetic nanofluid should present an irregular shape caused by like the diffusion or concentration gradient. And also there is insufficient experimental verification to verify or to evaluate their proposed model. So in this research work, we synthesize the magnesium doped gamma phase iron oxide magnetic nanofluids and fabricated the Agarosa gel. This magnetic nanofluid shows the high SLP or ILP and good biocompatibility. And the Agarosa gel that is very similar to the biotissue or human tissue. So after injecting this magnetic nanofluid into the Agarosa gel, we can obtain the spatial distribution or the real shape of the magnetic nanofluids inside the Agarosa gel or biotissues. So after obtaining the spatial distribution of nanofluids, so the concentration or temperature the concentration distribution and temperature distribution can be simulated and investigated. And also we used the experimental results to evaluate the validity of our proposed model and proposed methods to interpret and predict the physical and thermal behavior of magnetic nanofluids in magnetic hyperthermia process. So hopefully hopefully our simulation results and experimental results and the proposed model can provide valuable information and interpretation for our in vivo and animal experiments. So here is the experimental and simulation process, including the synthesis of magnetic nanofluids and the magnetic nanofluid injection process and a specific model for mass and heat transfer simulation. So after synthesizing the magnetic nanofluid, the particle size and the particle distribution and the magnetic properties were categorized. The particle size is around 30 nanometer and the particle distribution from TM is very homogeneous. And the magnetic nanofluid, this magnetic nanofluid shows superparamagnetic characteristics. That is a requirement for our next in vivo experiments. So here is the injection setup and injection modalities using single injection, single point injection, and 4 points injection. So after injecting our magnetic nanofluids into agarose gel, we can obtain the time dependence, the spatial distribution of magnetic nanofluid inside the agarose gel. So as we can see, the distribution of magnetic nanofluid in agarose gel shows in an irregular shape because of the diffusion or concentration gradient. So we believe this real distribution of nanofluid in agarose gel will be the basis for our next or for our subsequent mass and heat transfer simulation. So firstly, we consider the concentration distribution. Here, we simulated the concentration distribution under different diffusion time and using different injection modalities like 1 point injection and 4 point injection. By solving this convection diffusion equation, that is the main equation for our concentration distribution simulation. Because we know the temperature distribution was greatly influenced by the concentration distribution. So after determining the concentration distribution, we can easily get the temperature distribution. Here is the temperature distribution under different injection modalities like 1 point injection and 4 point injections under different diffusion time. As we can see, the 4 point injection methods, the temperature is more homogeneous and it covers more effective tumor areas. So this is beneficial for magnetic nanofluid hyperthermia application. So after simulation, we using the experimental result or experimental data to verify or to evaluate our validity of our proposed model. Like these two, A and B, these two figures are our experimental setup, and these two, C and D, is the temperature rising characteristics of agarose gel after injecting magnetic nanofluids. So these two, E and F, these two figures are the comparison results from like theoretically calculated results and experimentally obtained results. So the experimental results and simulation results shows very similar. That means our proposed model and methods are effective to interpret and predict the heating behavior of our magnetic nanofluid in magnetic hyperthermia. So after verifying or evaluating our proposed model, we investigated the influence of diffusion time and initial concentration on the temperature distribution to explore which parameter is more important in magnetic hyperthermia. Like here is the concentration distribution. On the top, that is under different diffusion time as a fixed initial concentration 20 milligram milliliter, and at the bottom that is under different initial concentration at a fixed diffusion time 2 hours. So after determining the concentration distribution, we also get the corresponding temperature distribution like here. From this temperature distribution, we can find the diffusion time. Like the diffusion time on the top, that is diffusion, that is under the different diffusion time. It can generate the diffusion time of magnetic nanofluid plays more important role in magnetic hyperthermia. That is because it can generate more homogeneous temperature distribution and covers more effective tumor areas.
2 minutes.
So after that, we conducted our in vivo magnetic hyperthermia experiments, magnetic hyperthermia performance test using the magnesium doped gamma phase iron oxide magnetic nanofluid. So we believe our previous proposed model and simulation results and experimental results can provide some important or valuable interpretation or information, like the injection condition or injection strategy for our in vivo or animal experiments. So here is the conclusion, like the 4-side injection method is more effective, and our proposed model and the simulation results were verified by our experimental results, and the proposed model can provide valuable information for the next or for the subsequent in vivo experiments. And we also found the diffusion time of magnetic nanofluid is more critical than the initial concentration of magnetic nanofluid during the magnetic nanofluid hyperthermia. Okay, thank you. Thank you for your attention.
Thanks for the nice talk. Any question from the audience, you can raise your hand and I can unmute you, or you can text your question in the text box. If there's no question, we can move to next speaker.
Now, okay, we are going to start with a presentation of Ruihao from Case Western Reserve University. So you can start whenever you want.
Okay, well, thank you for the introduction. And thank you to the organizing committee for this opportunity to talk about our work on tunable spin charge conversion in topological Dirac semimetals. Let me get my pointer. Okay, so this work is done in collaboration with Pantaushen and Shulei Zhang at Case Western Reserve University. We know that spin charge conversion has been an important theme in spintronics. In particular, the spin Hall effect is a well-known example of charge to spin conversion. And the origin of the spin Hall effect can be traced back to basically two mechanisms: the intrinsic one, which is related to the Barry curvature, and the extrinsic one is induced by disorder. So typically in topological materials, the Barry curvature gets enhanced due to the band topology. The intrinsic contribution will be dominant. And conversely, there's also the inverse spin Hall effect, which does the opposite, as the name suggests, converting a spin current to a charge current. So there has been several recent works on spin Hall effect in various topological Dirac semimetals, including these three references here. And along this line, we would like to ask the question that whether or not we can have tunable spin charge conversion in this class of materials. And we find that by simply applying an external magnetic field, we can achieve this goal, which I'm going to tell you in this talk. So I'll start by giving a very brief introduction to topological Dirac semimetals, or TDSMs. So these are the 3D materials which host Dirac points in their bulk. So the Dirac points are fourfold degenerate band touching points protected by time reversal, inversion, and uniaxial rotation symmetries, typically along the z-axis. So based on this reference here by Yang and Agarosa, these TDSMs can be broadly classified into two different types. So in type 1 TDSM, there's a pair of Dirac points on the rotation axis, as you can see from this schematic here. So the rotation axis is the z-axis. Whereas in type 2, there's a single Dirac point at the time reversal invariant momentum, or TRIM. So in our work, we'll be focusing on the type 1 TDSM, which has a pair of Dirac points. And two of the most popular materials are cadmium arsenide, which has a C4 rotational symmetry about the z-axis, and sodium bismuthide with a C3 symmetries. will employ a widely used low energy effective Hamiltonian for a typical type 1 TDSM. So if you write down the Hamiltonian in matrix form, you can see that it can be written in this block diagonal form with the spin up and spin down sectors. So in this sense, it's easy to think about the Dirac Hamiltonian as really two copies of Weil Hamiltonians, as shown in the schematic down here. So basically, if you isolate out the spin up or the spin down block, then each of them will be describing a Weil semimetal, which has two Weil points on the KZ axis. And these Weil points are twofold degenerate, and they come in two different chiralities, indicated by this blue and red colors. So now if you plot the Barry curvature for one of these bands in a Weil semimetal, you find something like this. So essentially these Weil points are monopoles of Barry curvatures. And the difference is that at one Weil point, the Barry curvature vectors point outwards, and at the other, they all point inwards, indicating that they have different chirality, which is usually characterized by the so-called Chern number of ±1. Now you can readily write down a spin Hall current because of a finite Barry curvature. So with the spin polarization in the z direction. So what you find is that it can be written as a spin Hall conductivity times E cross Z. So already you can see the spin Hall current here is anisotropic because it's maximized when the electric field is applied perpendicular to the Z axis, which is the rotation axis, and it vanishes when it's parallel to it. And what's more interesting is that the spin Hall conductivity can be written as a constant times KD, where 2KD is actually the separation of the Dirac points on the KZ axis. So this is really analogous to what's happening in Weil semimetals, where the anomalous Hall conductivity is also proportional to the separation of the Weil points in momentum space. So likewise, you can also write down the charge Hall current, and in this case, it vanishes because it turns out that the total Barry curvature in a Dirac semimetal is 0 due to the presence of both the time reversal and inversion symmetries. So in this case, there's a pure spin current in the Dirac semimetal. So now I want to turn on the external magnetic field, and I want to just briefly discuss the tunability of the spin Hall and charge Hall responses. And this tunability really comes from two factors, spin mixing and band topology, which I'm going to tell you now. So without any magnetic field, as I said before, both the conduction and valence bands are spin degenerate. And in this case, you have two Dirac points on the KZ axis. So now if you apply a B field say in the Z direction, because it breaks time reversal symmetry, it actually lifts the spin degeneracy of the bands. But in this case, each band is labeled with a definite spin, so there's no spin mixing. What it also does is that it splits each Dirac point into two Weil points of opposite chiralities. So now if you tilt the B field away from the Z axis, let's say to 101 direction, in this case, the bands become spin mixed in general. And what's more, there's 4 additional Weil points in the spectrum. So in total, there's 8 Weil points. And if you imagine tilting the B field from the Z axis towards the X axis, what happens is that these Weil points are actually getting closer together, indicated by these arrows here. So finally, when the B field is along the X axis, each 2 of these Weil points will merge into a single single Dirac point. So in this case, the system actually enters a Dirac semimetal phase once again. So we'll start with the relatively simple case when B is applied along the Z direction. So remember, in this case, there's no spin mixing. And the Zeeman coupling can be written as a sum of an orbital symmetric and an orbital antisymmetric term. So it turns out that they do something different. So the orbital symmetric term will actually split each Dirac point into 2 Weil points of different energies without changing their momentum. And the orbital antisymmetric term will shift the Weil point positions along the KZ axis, but they all happen, they all sit at 0 energy. So now you can compute the spin Hall and anomalous Hall responses coming from these 2 Zeeman couplings. So for the spin Hall conductivity, you find that both Zeeman couplings will give rise to a correction to the original spin Hall conductivity when there's no magnetic field. And this correction is proportional to h squared. And h here is the Zeeman splitting, so it's actually proportional to the magnetic field strength squared. And for the anomalous Hall conductivity, the orbital symmetric term does not contribute. And the antisymmetric term will give rise to a correction that's linear in H or linear in B. So in this case, because of a finite anomalous Hall conductivity, there's spin to charge conversion when you apply the B field. So for B in arbitrary directions, we can use this general Zeeman coupling. In matrix form, you see that because of the presence of Bx and By component, the total Hamiltonian would not be Bloch diagonal anymore. So the Z component of the spin is no longer conserved. So in this case, you should expect some unconventional spin Hall conductivity tensors to emerge, in particular with the spin polarization in X and Y directions. So we use the standard Kubo formulas to calculate the spin Hall and charge Hall conductivities. We have retained this band broadening factor, which is inversely proportional to the lifetime of the quasi-particle in a Dirac semimetal, which we estimate to be about 10 MeV. So here's the result of the spin Hall conductivity bit dependence. So in the first column here, these three graphs show the spin Hall conductivities with the spin polarization in X, Y, and Z directions as a function of the polar angle in spherical coordinates, as shown in the schematic here. So the three different curves correspond to different magnetic field strengths, 2, 4, and 6 Teslas. And the second column shows the spin Hall conductivity as a function of the azimuthal angle, phi. Basically, you are imagining rotating the magnetic field in the horizontal plane. And the three different curves correspond to different theta angles. So by these plots, you can determine the total B dependence of these spin Hall conductivities. So without getting too much into the detail, I just want to emphasize that, as you can see from these plots, the spin Hall conductivities is really tunable upon variation of the magnetic field direction. And in particular, both the direction as well as the magnitude can be tuned depending on the orientation. So similarly, you can do the same thing for the anomalous Hall conductivity. So in this case, it shows a simple BZ dependence in the low field limit, so which comes down to a cosine theta dependence without any phi dependence here. So lastly, I just want to briefly touch on the differentiation of the anomalous Hall conductivity from the ordinary Hall. Doing a sort of a simple back of the envelope calculation, assuming a relatively low carrier density for cadmium arsenide, you can calculate the B dependence of the anomalous Hall conductivity, assuming that B is applying the Z direction, for example. And you can see at relatively low fields, it shows a linear B dependence, but up until about 8 Teslas. So after that, because of higher order corrections, it starts to deviate. Whereas for the ordinary Hall effect, it's the B dependence is 1 over B. So you should expect that at high fields, the anomalous Hall contribution would dominate over the ordinary Hall effect. To summarize, we realized that basically the topological Dirac semimetals can provide another platform for realizing both electrically and magnetically tunable spin charge conversion, which actually arises from its unique band topology. So in particular, when there's no magnetic field, I show you that there's pure spin current coming from the spin Hall effect. But when you apply an external magnetic field, there's a finite anomalous Hall effect, which converts the spin current to the charge current. And we find that both the direction and the magnitude of the spin and charge Hall currents can be tuned by this magnetic field orientation. And one possible future direction is that we need to, so far what we did is confined in this low field limit, and a more careful investigation of the high field limit would be required in the future. Thank you.
Thank you, Ruihao, for the very nice talk. I would like to open the session to questions. If there are any questions, you can raise your virtual hand or write in the chat. Okay, I will start with one question. In slide 9, you discuss the variation of the conductivity as a function of field. Yeah, at the bottom left. it changed rapidly with the magnetic field, right? From 2 to 6, there is a huge change for me. Do you have any comment on this?
Yes, and that's because the spin Hall conductivity, as you can already see from this analytical results, it's proportional to the magnetic field strength squared. So that's why when you change from 2 to 4, it actually there's a square dependence here. Whereas for the anomalous Hall effect, it's actually linear, so you don't see such a dramatic change.
And at the end, you mentioned that you wanted to explore the limits or high field limit. What are the fields that you consider as high field? More than 6 Tesla?
Actually, the definition of high field depends on whether you're talking about the spin Hall or anomalous Hall, because we can see from this expression here, right? So it really crucially depends on the ratio between the Zeeman splitting and the m naught, which is a parameter factor, or in this case, there's also more parameter factors here. But so for the charge Hall, the high field would be actually would be higher because there's no squared suppression. Whereas for the spin Hall, you have to. Sorry, for the spin Hall, the high field will be higher than the anomalous Hall because there's a square suppression here from this factor.
Okay.
Yeah.
Okay. Thanks. Thank you, Ruihao. We can proceed to the next next speaker.
Hey, so our next speaker is Agustin PEDROSO from Argentina.
Hi, thanks for the presentation. Please tell me if you can see my screen.
Yes, you can see it clearly. You can go ahead and get started.
Okay, good. So first, I will thank the organizer for giving me the opportunity to present my work. As the title of my presentation said, I will talk about the strain-induced magnetic transition in calcium manganese ultra-thin films. Let me change to the laser. Yes. Well, we'll start with a knowledge of my talk. First, I will describe a little bit about this material, the most important thing that you need to know in order to understand the results. Then I will describe the result we obtained. I will focus on, in particular, with experimental measurements and characterization that we done, but also we'll talk about the ab initio calculations. Then give some conclusions and perspective for the future. So starting with the description of the material, it's a perovskite type oxide that crystallizes in orthorhombic crystal structure. This is a schematic representation of this material. These are the lattice parameters of the orthorhombic structure, but it's important to mention that this structure can be described in the pseudocubic approximation with a cubic lattice parameter of around 3.72 Armstrong that I will use it a lot in the next slides. It's an antiferromagnet in bulk. In particular, it's a G-type antiferromagnet with a near temperature of 120 Kelvin. Here, the black arrows represent the magnetic moment of the manganese ions in the G-type configuration. It's important to mention that the alignment of the moments is not perfect. It has a small angle that gives rise to a weak ferromagnetic moment of around 0.04 bond magnetons per manganese ion. So starting with our samples and our results, all the samples I will show you to you in this work were grown by PLD onto STO001 substrates. And we changed the thickness in for the different samples between 3 and 30 nanometers. It's important to mention that the mismatch between the STO and the CMO, if we take into consideration the pseudocubic lattice parameter of the CMO, is around 4.7%. That this value will be important in the next slide when we analyze in detail what is happening with the crystal structure. And we analyze in detail what happened with the surface, the crystal structure, and the magnetic properties. Starting with the surface characterization, we perform IFM measurements and also read measurement after the position of the sample in situ. From this result, we were able to determine that we have a very flat surface with low roughness. The roughness that we estimate from the IFM images was below 0.5 nanometers, which is good for our characterizations. And also we obtain similar results for the different samples. Not matter the thickness of the sample, we obtain the similar characteristic from the surface of the sample. So if we continue the analysis and see what happened with the crystal structure, in order to do this, we analyze in detail high resolution TNA images that allowed us to see what happened, especially near the interface between the substrate and the film. These are the kind of images that we obtained. This is particularly for the 3 nanometer samples. From these high resolution TMA images, we were able to identify 2 regions in the samples that we call CMM1 and CMM2. Here are marked with this black white dotted line, marks the first region, which is closest to the substrate, and the second region, which is above the first one. These regions are characterized by a sharp discontinuity of the lattice parameter. If you analyze what's happening very close to the interface in the first region, we observe that we have a crystal structure that is almost cubic, with an average lattice parameter of 3.93 angstrom, which is considerably higher than the value of the bulk, but is pretty close to the value of the substrate. So the first atomic layer of the CMO tried to copy the crystal structure of the substrate. If we move on and we analyze what is happening in the second region, which is above the first one, we observe that both parameters, the in-plane and the out-of-plane, relaxes. If we compare, for example, what happened with the in-plane lattice parameter just above the interface between the first region and the second region, we observe that we have this value of 3.88, and if we analyze what happened very close to the surface of the film, we observe that considerable reduction of the lattice parameter. So the system is trying to relax. And we observe a similar result in the case of the out-of-plane lattice parameter. In both cases, when we are far away from the surface, with the interface between the substrate, the lattice parameter relaxes and trying to approximate the bulk lattice parameter. If we move on and analyze what happened with the strain, with this image, we were able to measure the strain across the sample in 2 different directions, in the in-plane and the out-of-plane direction. And when I analyze what happened with the strain field, here the bright colors indicate positive strain and the darker colors indicate negative strain. And this black dotted line indicates the interface between the substrate and the film. As we can see in these images, we will see that the first layers, this region very near to the interface between the substrate and the film, more or less have the same strain field, which indicates that this structure tried to copy the strain of the substrate, which is consistent with the estimation of the lattice parameter in the first region. And then we have a more complex strain field, which is consistent when we come with some columns or other kind of type of growth. And if we analyze what happened with the out-of-plane configuration, with out-of-plane strain, we observe that just above the interface, we have an increase in the strain considerably, and then a sharp reduction and a progressive relaxation of the film, which is consistent with the estimation of the lattice parameter that I mentioned before. So from these images, we were able to determine that our crystal is clearly distorted if we compare this structure with the bulk. And these changes in the crystal structure could have a major impact in the magnetic and electric properties of these kind of materials. Another thing that is worth mentioning is that we observe an excess of manganese ions, especially at the interface, just in the first atomic layer, but then if we analyze what is happening with the stoichiometry of the sample in this region, we observe the expected values. So if we move on and analyze what happened with the magnetism of the sample, in order to do this, we perform magnetization loop at low temperature for all the samples. This in particular the result for the 3 nanometer samples at 10 Kelvin. From this result, we were able to determine that we have an easy plane in the plane of the sample. And also we analyze what happened with the saturation magnetization for the different thickness at the same temperature. This is the plot that we obtained for the saturation magnetization for the different samples at 10 Kelvin. And there are several things that is important to mention from this graph. The first thing is we observe that we have an enhancement of the saturation magnetization if we compare these values, all these values with the bulk. The bulk has around 0.04 Bohr magnetons per manganese ions, and all the samples that we analyze have a considerably higher saturation magnetization. For example, if we compare what happened with the thinnest sample of 3 nanometers, we have a saturation magnetization of 0.67 Bohr magnetons per manganese ions, which is more than 10 times larger. Another thing that we notice from these samples, that if we increase the thickness of the sample, the saturation magnetization reduces. well, in order to understand a little bit better what is happening, which is the origin of this enhancement of saturation magnetization, we perform ab initio calculations in two different configurations. One field of 3 nanometers relaxed without any kind of strain, and one field of 3 nanometers calcium manganese, but we impose the lattice parameter of the STO in the in-plane direction. And we calculate which is the more stable magnetic configuration in each case. We perform more characterization, but I don't have enough time to talk about that. If you're interested, you can find all the details in our paper. So from this result, as expected, we observed that the most stable magnetic configuration in the case with a relaxed system is the G-type, as I mentioned before in the bibliography. But if we analyze what happened with the strain field, we observe that the most stable magnetic configuration is the E-type antiferromagnet. The E-type antiferromagnet is different from the G-type. In the E-type, we have a ferromagnetic coupling in the plane and antiferromagnetic coupling between planes. So the tensor strain can induce a change in the magnetic configuration, and if we take into account the low dimensionality of the sample, this could give rise to a net magnetic saturation magnetization of around 0.16 Born magnetopermanganese ions in the case of the 3 nanometer pin. So in both cases, we observe an enhancement of saturation magnetization due to the strain, but we have a discrepancy between the experimental and the calculation values. The origin of this discrepancy, we are not so sure yet. We have several theories in order to explain this. One possible theory is that the manganese ions at the interface can contribute with some spurious contribution in the saturation magnetization. Another is that the simulation did not take into account all the complex behavior that we observe in the crystal. We have these two different regions with really different crystal structure. So we are trying to understand, performing more simulation, and also trying to change a little bit the parametric growth in order to improve the growth. So to conclude, the effects of the Hansen strain and low dimensionality were analyzed. From the experimental point of view, we are able to determine in detail what is happening with the crystal structure from the high resolution TMM images, especially near the interface, and which we were able to identify these two different regions on all the deformation of the crystal structure. And also we were able to measure ferromagnetic hysteresis loop at low temperature, and also we observed the enhancement of saturation magnetization that I mentioned previously. From the calculation, we observed that only the strain can induce a transition from the G-type antiferromagnet to an E-type antiferromagnet, which could lead to the appearance of an enhancement or enhanced saturation magnetization signal that I mentioned previously. But more experiment and calculation are required in order to understand better what is happening, in order to see if you want to use this for possible application in, I don't know, for antiferromagnetic spintronic, for example. The system could be very interesting due to the properties that it has. And some perspective, some measurement that we are doing right now. For example, we are analyzing other substrate, for example, aluminum lanthanum, in order to understand what is happening when you have a different kind of a strain. And also we are performing electric characterization in order to get more insight about the properties of the field. And we obtain some promising results when we analyze the magnetoresistance. But we are trying to understand a little bit better what is happening, but I hope so that I can share those results in the near future. And we continue with other substrates, for example, manganese oxide and STO with another crystal configuration, and more complex heterostructure in order to induce a strain using electric field, for example, in this kind of material, using a ferroelectric below. So to conclude, I want to thank the financial support from different organizations, and thank you for your attention. And I open to questions.
Thank you, Agustin. Is there any question in the audience? You can raise your hand, and we will bring you to this to speak up.
Actually, I have one question. Can I
Yes.
go ahead, Jason?
Yeah, go ahead, Luis.
Would you expect that the thickness of region 1 in the TEM images that you showed have a dependence on the total thickness?
No, because we performed a similar experiment with similar DMH experiment in sample with different thickness, and also they have the same thickness.
Okay. I suppose you grow the samples under an annealing, right?
Yes.
Okay.
Yes.
What temperature do you use?
For the growth of the sample, 700 degrees Celsius, and then for the annealing, 400.
Okay. So you do a post annealing after
No. After the deposition, we turn off the heater and raise the oxygen pressure in order to ensure that we don't have too much oxygen vacancies in order to avoid that.
Okay, I understand. Thanks.
Yeah, welcome.
Thank you. Thanks a lot, Agustin. I think we can proceed to the next speaker.
Yes, we are on time. The next speaker is Lucas ALBORNOZ from Instituto de Nanociencia y Nanotecnología from Argentina. Lucas, do you want to share your screen, please?
Hello.
Hello, we can hear you. And if you want to put your full screen, yeah, okay. You can start whenever you want.
There you hear me well?
Yes. Go ahead.
Okay. Hello, my name is Lucas ALBORNOZ, and I'm pleased to participate in this conference. In this talk, I will show you some of the results we have obtained in the framework of my PhD thesis, which I'm doing with the joint supervision of Vincent Jedy of University Paris-Saclay in France and Javier Curiale at Instituto Balseiro in Argentina. And this work is about the experimental study of the universal critical exponents of the depinning transition of magnetic domain walls in thin films. I will start with an introduction on the depinning of elastic interfaces in disordered media. Then I will talk briefly about the studied sample and the experimental technique we use. Then I will show you some results on the magnetic domain wall dynamics at low temperatures and how we determine two universal critical exponents of the depinning transition and a comparison with theoretical predictions for these exponents. Finally, I will conclude. In nature, there are many interfaces which may be seen as elastic interfaces which lie in disordered media. And here in particular, I show you some examples of interfaces which may be seen as one-dimensional elastic interfaces which lie in a two-dimensional disordered medium. If one tries to see what are the dynamics of one of these interfaces when they are subject to a uniform driving force, one can see that the velocity as a function of the force follows a behavior which is schematized here. In particular, if there is no thermal energy or at zero temperature, there is a range of low forces where the interface is pinned, while above a characteristic depinning force, the interface moves. And the dependence of the velocity with the applied field follows a power law, which is characterized by a critical exponent, which is this beta exponent. And in this depinning transition, as it is usual for phase transitions in the framework of statistical physics, there also exists a correlation length, which in this case is associated to the size of characteristic events which make the interface move. And this correlation length, which is this one, diverges at the depinning transition, and this divergence is characterized by another critical exponent, which is this one. In this work, we experimentally study these two power laws and quantify experimentally these two critical exponents. The importance of these critical exponents is that they characterize the universality class to which the studied phenomena belongs. In particular, for magnetic domain walls in thin films, two different universality classes are usually considered. And there are open questions regarding to which one of these magnetic domain walls in thin films, and particularly the depinning of magnetic domain walls in thin films, belong. Here I show you the values of these two exponents and other critical exponents for these two different universality classes. And as we can see, these values are different. So with a good experimental characterization of this transition, we may differentiate between these two and say which one of them better describes the phenomena of magnetic domain wall depinning. In this work, we study a gadolinium iron cobalt thin film, which is a ferrimagnetic material, and it has a thickness of 10 nanometers. We observe this film and the magnetic domains and their dynamics with the polar magneto-optical Carrier effect microscopy. And by applying a magnetic field, which is the uniform driving force in our case, we observe how these domain walls move. And we obtain curves of the velocity as a function of the applied field. As you can see, these two curves that we have obtained are very similar to the theoretical prediction that I have shown before. In particular, for 20 Kelvin, we observe a behavior which is quasi-athermal. It is a zero temperature-like behavior, and this qualitative observation is already very important because it's the first time the zero temperature-like behavior, the pinning transition of magnetic domain walls in particular is observed. Normally in the laboratory, the most easily observed behavior is the thermally activated behavior. So in order to obtain this beta exponent, we perform a fit of the pinning law for zero temperature, which is this one. For different temperatures, we observe that for all these temperatures, this law successfully describes the observed behavior, and we obtain values of the beta exponent for all these temperatures. As it is a universal critical exponent, we expect to obtain, to have a unique value, and then we compute a mean value which is consistent with all the obtained values. And then, in order to obtain another critical exponent, we quantify the correlation length in these same conditions of low temperature. In order to do this, what we do is to compute the velocity correlation function, considering that the velocity of 2 points in the domain wall is correlated only if their movement is done via the same avalanche events. So, well, taking into account this idea, we obtain values for the correlation length and fit the power law that that relations the velocity and this correlation length. We observed that the expected power law for zero temperature is also consistent with the obtained results, and we obtained again a value for the characteristic critical exponent. Then now we compare this with the expected values of the critical exponents that I have shown you before. And as we can see, the Kensth-Edwards-Wilkinson universality class is the one that successfully describes the behavior we have observed, because the values of the critical exponents is in accordance with these values and not with these ones. So we have measured velocity versus field curves at low temperatures. This allowed for an observation of an athermal behavior. This is the first observation of the depending transition in these conditions in magnetic domain walls. We could therefore directly observe and characterize the depending transition using predictions for zero temperature. We fitted this law, the pinning law, and obtained a value for the beta exponent. Then we could quantify the pinning correlation length by measuring the velocity correlation function. And we obtained also a value for the critical exponent, which characterizes the divergence of the correlation length. And we finally can say that the pinning of magnetic domain walls in thin films is better described by the Kensth-Edwards-Wilkinson universality class. Thank you very much for your attention.
Thank you, Lucas, for a very nice talk. I would like to open the session to questions. If there are any question, please raise your hand or write it in chat. We have some time, so in the meantime, I would like to start with one question from me. Sample seems to be of very high quality. However, I would like to know if you had some problems with the pinning center or defect that influence on your measurement of the velocity.
There are some, yes, some strong pinning centers, but we have focused. We have made all our studies in the same region in order to have the same kind of inhomogeneity, and in the region in which we measured domain wall velocity, there were no strong pinning centers.
Is there a way to subtract or to remove this influence in case you have some pinning center? How do you avoid the influence of this in case you have this in your measurement?
I think that if you have too many, then it is very difficult to study this in the framework in which we are studying this, because we consider that the disorder is rather weak.
Okay.
Yes, but in this sample, we have found some regions where no strong pinning centers exist, and then we could do our studies well with no problems.
Okay, I understand. Thanks. We are on schedule. We have time for more questions if you want to ask to the audience. From the audience, I mean. If not, thank you, Lucas, for a very nice presentation. We can move on. Jason, if you want.
Yes. The next speaker will be Alexander from Massachusetts Institute of Technology. Alex, you can go ahead and share your screen.
Okay. How does this look? Can you hear me okay?
This looks great.
Great,
Yes.
thank you. Hi, everyone. Thanks for coming to listen to my talk today. My name's Alex Kosak. I'm a PhD student in the Department of Material Science and Engineering at MIT. Today, I'll be talking about our recent work on the voltage modulation of the RTK interaction using a magneto-ionic gating platform. So the use of voltage control for other magnetic properties, namely anisotropy, is very present in the literature already. Two examples in which people have used the voltage to control magnetic anisotropy has been the electric field and the magneto-ionic effects. And in these devices, the aim is to change the magnetic anisotropy in a way that you can modulate the magnetization of the magnetic material from in plane to out of plane. And while this is able to achieve 90-degree switching of a magnetic layer, it's not able to achieve 180-degree switching. So if you wanted to make a device in which you're using the voltage to control 180 degrees field-free switching of, for example, magnetic memory, we'll have to look at a different magnetic effect. And so for that reason, we look at RKKY coupling. So for those not familiar, the RKKY interaction in magnetic multilayers has been well studied. And for example, here it's shown for a cobalt, ruthenium cobalt magnetic multilayer. So it's an indirect exchange interaction in which the conduction electrons oscillate the spin polarization between two magnetic layers. And so this oscillation decays and switches between ferromagnetic and antiferromagnetic depending on your interlayer thickness. So you have two ferromagnetic layers that are separated by a non-magnetic spacer layer. And so when they're ferromagnetic coupled due to the RKKY, you'll see a single hysteresis loop with a single switching event here. And when they're antiferromagnetic coupling per field speed direction, there'll be two switching events in which each layer is switching independently. Now, ways that people have used to try to modulate the RKKY interaction has been the electric field, for example, where the electric field is used to create charge accumulation at the interface, and this would modify the Fermi wave vector, therefore changing the RKKY shine and strength. However, if your material is made out of a metal, it's quite difficult, as many people know, to have an electric field inside a metal. And in experimental work of this effect, it's shown that it's a quite small effect, and so wouldn't be able to achieve robust switching of 180 degrees. In the field, there's also been liquid ion gating attempts where people use a liquid electrolyte to apply an electric field, and that led to, again, charge accumulation at the magnetic material. And they were able to show that they could switch from antiferromagnetic to ferromagnetic devices, but the reversibility of this was limited. In addition, if you're looking for a solid state approach, you're gonna have to get rid of that liquid electrolyte. And so another effect that people have looked at is magnetoelectric, where they apply electric field to create a stress in the piezoelectric device, in this case is PMMPT, and that would cause a strain in the magnetic material and thus change the coupling from antiferromagnetic to ferromagnetic. However, in this case, it was not only in plane, but also they had to use an applied field in order to get the switching. So to get a field-free 180-degree switching, just using a voltage control the RKKY, we'd have to use a different platform. And so that's why we've been working on this solid-state hydrogen ion gating. So again, this is a voltage-controlled mechanism. It has a much lower power consumption than your current control techniques. And we use the magneto-ionic switching effect by solid-state proton pump gating that's been shown previously for the control of things like magnetic anisotropy and exchange bias. So how it works essentially is that ambient water that's in the atmosphere is split at the interface with an applied voltage, the interface of gold in the atmosphere, and then protons are driven through a proton conducting oxide, and then they're reduced hydrogen at the interface of the magnetic material. And this can modulate the magnetic anisotropy from out of plane to in plane. It's reversible. And the reason we're using hydrogen as opposed to other ions for magneto-ionic gating, for example, lithium or oxygen or nitrogen, is because hydrogen has been able to show quite high cyclability for a gadolinium cobalt device up to 10,000 cycles. It's quite reversible and stable. Hydrogen is one of the smallest ions, so it can lead to some of the rapidest and quickest effects. And it's also CMOS compatible. There's been some work on hydrogen modulation of the RKKY previously in the literature, namely for iron niobium superlattices, where they've been able to show that you can switch the RKKY coupling from antiferromagnetic to ferromagnetic reversibly by using a few atomic percent of hydrogen in gaseous form to reduce the switching. they were able to definitively show again that this hydrogen actually changes the Fermi wave vector, which changes the RKKY. And it wasn't that hydrogen was, for example, changing the lattice constant of the ruthenium interlayer, as they saw with polarized neutron reflectometry. But again, for a device in which you're an on-chip device, a memory device, you're not going to be wanting to inject gaseous hydrogen. You want some type of solid state approach. So for that reason, we've designed this RKKY coupled synthetic antiferromagnetic that's made of a cobalt platinum multilayer separated by another magnetic layer using a ruthenium interlayer wedge that we grow so the ruthenium has a variation thickness across laterally of our sample. And the top magnetic layer is a cobalt palladium multilayer. And then we have our proton conducting gadolinium oxide and a gold electrode. And so the reason we're using cobalt platinum multilayer here is because we want to be able to control the coercivity to make it extremely low so that it's a quite good free layer, easy to switch. And the reason we're using cobalt palladium multilayer up here is because palladium has a quite high diffusivity to hydrogen relative to platinum. So we can still get the hydrogen all the way through into our ruthenium layer. And we need to use a cobalt palladium multilayer because we need to maintain, again, this good magnetic, perpendicular magnetic anisotropy. And as previously shown, that hydrogen can actually modulate quite well the anisotropy of cobalt palladium and cobalt platinum multilayers, or cobalt platinum layers. So we had to make this a multilayer in order to make the anisotropy robust. And we can have used a sensing layer, namely gadolinium oxide, instead of cobalt platinum at the bottom to ensure that the hydrogen is actually getting all the way through. And it has no problem reaching all the way to the ruthenium, as we see here in our sensing layer. And so we can gate these layers individually here, the cobalt platinum and here the cobalt palladium, to show that individually that the anisotropy remains quite robust to the proton gating. So in a typical experiment, what you want to do now is measure the RKKY coupling as a function of the ruthenium thickness. And traditionally, for a symmetric synthetic ferromagnet, where both you have two symmetric coercivities and saturation magnetizations of your layer, you would just take this first switching event and the second switching event to find the exchange field, and you can use the exchange field along with your saturation magnetization, your thickness, in order to get your exchange coupling constant J. And that's for when it's anti-ferromagnetically coupled layers. When it's ferromagnetic coupled, all you get is a single loop. So you don't get any splitting, and because of that, you won't be able to quantify your exchange field, and so you just, most of the time plot is a 0 or unknown or dotted. However, the advantage of when using a non-symmetric synthetic antiferromagnet in our case is that we can collect both a major loop and a minor loop. And when collecting this both major loop and minor loop, we can still use the same process for the minor loop. Now, in the minor loop, we again use the two switching events for that single layer to find the exchange field and the exchange coupling and the coercivity. And we can use the exchange field and the coercivity to then quantify our RKKY coupling constant between our two magnetic layers. And the advantages of the minor loop, where one layer in this case is pinned, which is our cobalt palladium layer on top, and the bottom cobalt platinum layer is free, is that we can not only quantify the anti-ferromagnetic coupling of our heterostructure, but we can also quantify the ferromagnetic coupling. So while the major loop may appear that there's still two switching events per sweep, and you may think that it's anti-ferromagnetic coupled, it's in fact ferromagnetically coupled layers, because if you look at the minor loop, you can see that the exchange field is actually shifted to a negative field, meaning that the coupling between the two, the free layer and the pin layer, is actually ferromagnetic. And so the advantages of having these two layers that are non-symmetric and have very different coercivities is that one can use the minor loop to quantify both the exchange field, both the ferromagnetic and the anti-ferromagnetic exchange field, and therefore their respective coupling constants. And this works for as long as that the coercivity of the soft layer plus that exchange field is less than the coercivity of the hard layer for quantifying ferromagnetic coupling. Otherwise, if it's greater than the hard layer, will just switch with the soft layer and you'll just see a single hysteresis loop. So now we can do those measurements where we're collecting the minor loop, and from now on, I'm just going to be talking about the minor loop measurements. We can quantify those minor loops as a function of the ruthenium thickness and see our classic oscillation of the RKKY coupling for different ruthenium thicknesses. It's decaying as a function of the ruthenium thickness increases and oscillates between antiferromagnetic and ferromagnetic. And we can pick out two individual points along that wedge again, where we have anti-ferromagnetic coupling on the top blue loop and ferromagnetic coupling here at the top in the red loop, and collect both major and minor loops. Now what we can do is then apply a gate voltage to our device. So we start with a device here that's in the ferromagnetic case, and we apply a positive gate voltage of 4 volts for 15 seconds. We can actually switch that ferromagnetic coupling to anti-ferromagnetic coupling. And this change field not only changes by 50 Hz, but also changes sign. And we can demonstrate that by applying a negative bias or 0 volts short circuiting the device, that we can recover it fully to the ungated state. And this works both ways. So if we start with another device, in this case, it's anti-ferromagnetic coupled to loop shift to the right, we can gate it to a ferromagnetic coupled state and back to an anti-ferromagnetic coupling state. So we're switching the coupling between the two layers, between anti-ferromagnetic and ferromagnetic, as long as we're starting at a reasonably close place to the switching point. We can push this device, as many have done with proton gating, down to quite fast switching timescales. So far, we've been able to demonstrate that with an ungated state for a 15-volt pulse at 750 microseconds, we can switch it into an ungated state. And so other proton gating platforms have been able to show down to 50 microseconds, 5 microseconds. So there's no reason probably that this, with some optimization of the heterostructure, that this can get even farther. And this is also quite reversible and cyclable. Up to so far, we demonstrated that this can be done for 40 cycles. And so now we can gate along the whole wedge of the sample, and we can show that a few important things come out. That this leads to, one, an overall decrease in the oscillation amplitude of our KKY coupling. It also leads to a phase shift, which you can see here in the inset. So that allows for a given ruthenium thickness for us to switch from the ferromagnetic state to the anti-ferromagnetic state. And as the ruthenium thickness increases, the effect becomes a little bit weaker. And now we can make a prototypical device out of this. So we can start with the hysteresis loop and saturate our sample to the positive state. So we saturate our sample to the positive state, and then we can do a positive field pulse. When we do a positive field pulse, we see that there's no switching in the MOC signal. And when we do a negative field pulse, we can see the switching. So with no applied voltage, we can see that that the minor loop is saturated in the positive state, and there's only switching when we have a negative pulse. And now when we apply a gate voltage, we can again start with the positive pulse to saturate our material at the top state. We then gate our device, and we know that our device switches without a field applied, because now when we do the interrogation, this positive field pulse, that's where we see the switching in the MOC signal. And there's no switching in the negative signal. And we can quantify the amount of switching in the MOC based on the relative difference in the MOC signal before and after the switching event. And we can see that's it's pretty stable up to 20 cycles before it starts to decay. And with that, I'd just like to thank the funding and my supporters, and I'm happy to take any questions.
Thank you so much for the great talk. Now the podium is open to questions.
I have a question, Alexander. Can I go, Jason?
Yeah, please go ahead, Luis.
I don't know. SAF are commonly used in MTJs, so I know that the voltage you use here are different from the ones that you use in a magnetic tunnel junction, close to below or close to 1 volt. Do you think this can influence on the reading or the lecture of an MTJ?
If I were to integrate this with an MTJ, would the applied voltage on the synthetic antiferromagnet influence the MTJ? Is that what you're asking?
Yes.
No, I think you can sufficiently decouple them, because you're only applying that voltage across the oxide layer. So the voltage is only going between this top layer of the gold electrode and the bottom of the oxide. So as long as you can control it, as long as you have enough oxide barriers between that and the MTJ, you shouldn't be changing anything with the MTJ.
Okay.
Purnima, you can go ahead and ask your question.
Hi, thanks, Alexander, for a great talk. I'm curious how much water needs to be in the atmosphere to actually be able to be pulled into this device, right? Because a lot of devices you want to kind of be isolated? Do you have to like prepare them in any way, or you're just kind of using these in an ambient atmosphere?
Yeah, that's a good question. We haven't gone through the process of actually quantifying, for example, the humidity needed in order to make our conducting our platform work. We know that it works out down to at least 20% humidity, but I don't do anything special to prepare the devices. I sputter them and then I take them out and go ahead and use them. There's no preparation other than that.
Okay, thank you.
Is there any other question? We have a little bit of extra time since the next speaker did not show up.
Yeah, we are on schedule now. I don't know if Carlo Tamanaja is in the audience. I think he's not. In that case, I suggest to proceed with Patricia. Patricia, are you ready? Patricia wrote me a few moments ago saying that she was ready.
Thank you. Now I can talk.
Okay. Do you want to go ahead, Patricia?
Yeah, sure. I
Okay.
can do that. Let me see if you can see my screen now.
It's loading. Yeah, we are seeing your screen and we can hear you clearly.
Great. So I just start?
Wait, I'm going to present you.
Oh,
yeah. Okay, now our next speaker is Patricia Rivas Rojas from Universidad Nacional de San Martín, from Argentina too. And she will talk us about AC versus DC temperature dependent magnetization measurement. So you can go ahead, Patricia.
okay, thank you very much for that introduction. My name is Patricia, and I'm going to show you just a little bit example of what I did for my PhD thesis in the Faculty of Engineering of the Universidad de Buenos Aires regarding the AC versus DC temperature dependent magnetization measurements, and more specifically, the effect of size and dipolar interactions on the energetic parameter analyzing magnetic nanoparticles real systems. So as a short introduction, I want to recall the difference between real systems and ideal models that we typically employ to analyze magnetic properties. We have in real systems size distributions instead of single size nanoparticles. We have a specific crystallinity associated with the material that we are employing instead of single anisotropy axis. It can have a single anisotropy axis, but it can have more. And also on the crystallinity depends the possibility of current rotation of the magnetic moment of the nanoparticle. And we also can embed these nanoparticles into a surrounding matrix that can avoid interactions related to direct exchange interactions, or some matrix mediated if we employ the right media. And also, if we can control the distance between the nanoparticles with this matrix, we can also control the polar interactions. So what it's important to remember about all these characteristics are that they are very important in the anisotropic constant of the system that basically controls the activated process of going from blocked to unblocked or superparamagnetic state in the system. So there are typical measurements related to AC and DC magnetization, and I'm going to show you a little bit what we did to analyze them. So what we did experimentally to control the size and interparticle distance of the nanoparticles was to obtain, through high temperature thermal decomposition of organic precursors, iron oxide nanoparticles coated with a lake in hexane, which resulted in pretty ferrofluids like this one. And what we did was, with controlling some synthesis parameters, we obtained two different sizes. And this way we can control from the dipolar energy the magnitude of the magnetic moments of each nanoparticle, since it is directly related to the volume of the nanoparticles. And we did a characterization using TEM and X-ray diffraction, where we could observe that the crystalline composition of the nanoparticles was the spinel structure, which we related to magnetite, but can also be a combination of magnetite and magamite. And we see that controlling the parameters, we obtained two different sizes. So afterwards, through inverse microemulsion method, we did a coating of each nanoparticle with a silica shell of different thicknesses, so we could achieve also control in the interparticle distance that we will call so on DCC. And this is the kind of samples that we finally obtained. So going to the structural and morphological characterization, we analyzed the main peak of the X-ray pattern with Scherrer equation, and we find the coincidence between this size of the crystallites through X-ray diffraction with the size obtained by TEM. So we can assume that each nanoparticle is a monocrystal. And what we also obtained was the distances or the thicknesses of each shell. So what we wanted to check if we were below an empirical limit of negligible interactions that is obtained through this equation, and for spherical nanoparticles is about 2.4. And what we can see is that for this cohort, I'm going to talk about S and B as small and big core nanoparticles, that for the small core nanoparticles, we reached and went way above that limit, while for the big core nanoparticles, we were right in the limit of 2.4 of considering the dipolar interactions. So going to the magnetic measurements, we employed typical routines of zero field cooling magnetization, where we observed the typical behavior of superparamagnetic systems in all cases. And since we have a real system, we have to think about the distribution of sizes. So we didn't analyze directly the information from the curves, but translated it to an activation energy distribution or a blocking temperature distribution. And what we can see is that as interactions are bigger, also the position of the peak and the broadening of the peak is shifted towards higher temperatures or higher activation energies. This is a very well known and expected for more interacting nanoparticles. So we observed the same tendency both for the small and the big core nanoparticles. And what we did was take the blocking temperature for each nanoparticles and into a interparticle distance inverse cubed relation. So we found a blocking temperature for the system in a limit when there are no interactions, and an associated or an equivalent dipolar temperature for each sample. So this is how we are going to represent our blocking temperature in each case. So with that value of dipolar temperature, if we want to call it some way, we subtracted it from the distributions that we previously obtained. And we can see that for the big core samples, we find the same position of the peaks and almost also the same shape of the peaks. While for the small core samples, we have small shifts between the peaks, the position of the peaks, and also a broadening effect. So we can assume that this is not only attributed to interactions, but also to surface effects. So there is an easy or a typical way of addressing surface effects that is related also to temperature-dependent saturation magnetization analysis, and it's applying the Bloch's law, which includes a term in here that addresses the effect of canted spins in the surface related to surface effects given the small size of the nanoparticles or breaking in the symmetry in the border of the nanoparticles. So we analyzed each sample. For the small samples, we can analyze all of them with this function, but for the big core samples, we can see that collective effects hinder the possibility of seeing the surface contribution, and even for the intermediate interaction nanoparticles, we can only apply the typical Bloch's law and not the modified one, which accounts the superficial effects. So the next typical analysis that is done for AC measurements is the magnetic susceptibility. And this we analyze with the Neil-Arrhenius law, which doesn't include dipolar interactions or any other type of interactions in the analysis. So we employed correctly the Vogel-Furger analysis to address for that component that I'm going to rewrite it here this way to resemble the previous function that we employed for DC magnetization. So looking at the numbers, what we can see is that analyze DC data, we obtain an inverse of the cube interparticle distance dependence for the blocking temperature, which leads us to think that this is all dipolar contribution, and we could from this obtain an estimation of the blocking temperature in a ideal absence of dipolar interactions. From Bloch's law, what we could see is that the freezing temperature related to the surface contribution was really small, so it should disappear rapidly with increasing temperature, and also that the information that we can obtain from the for the big core samples, it's not trustworthy since it presents weird parameters. If we want to say it somehow, it should be, for example, the B factor should be closer to bulk values, and it's far further than the sample. But for the small samples, we can extract interesting information, and it's important to see how the surface contribution goes lower as the interactions increases. So we should check how this is interacting, to put it in a way, and going directly to Vogel-Furger, because we know Neil-Arrhenius doesn't consider dipolar interactions, and we are sure we have the polar interaction effects. We can see how we obtain both tau zero and activation energy values that are as expected, bigger for the big cores and in the right order of magnitude. And also we can see that the T0 that we can obtain for Vogel-Furger is a bit bigger than the T related to dipolar interaction. So what we conclude is that surface effects as well as dipolar interactions manifest in the same temperature range and have exactly the same effect on spin relaxation rate approaching the critical temperature. So we expect that for Vogel-Furger and other dynamic analysis, the response will be a combination of both effects and not only one. So what we have here is a competing effects fight, something like this, the same temperature range, and they manifest themselves in the same manner. So it is we address them here to dipolar interactions, since we can control them with the silica shells, and also to surface effects that manifest in the modified Bloch's law. And we want to reinforce the fact that AC/DC magnetization are typical techniques that are reported in literature, but rarely are compared, and this is not always taken into consideration when analyzing the systems. And it's important to recall the valuable and complementary information that was obtained combining techniques and model. Also, it would be great if we could perform for this samples most power analysis, so we can address the real contribution to the effective anisotropy. And something I didn't stand up, but we did simultaneous analysis keeping shared parameters since we knew the common parameters between the same core samples, and this allowed us to avoid most of correlation when fitting procedures. So I want to thank you very much for your kind attention, and special thanks for the organizing committee and all the funding and support institutions that participated on this work. If you have any questions.
Thank you, Patricia. Thank you for a very nice talk. I would like to open the session for questions. If you have any question, please write it down in the chat or raise your hand. There is one question from Rod Goldfarb. Please go ahead.
Hello, Patricia. Very nice presentation. Your data plots are expressed as normalized magnetization.
Yeah.
Is that because of the difficulty in knowing the volume or mass of the magnetic particles?
More precisely, in knowing the contribution of the silica shell. I mean, it's not contribute. It doesn't contribute magnetically, but in the final mass that we can measure. So it should be reported as a function of mass, but it's not easy to measure. What's the magnetic nanoparticle contribution and the silica contribution?
So what is the normalization with respect to?
Okay, I was going there. So what we did was normalize by the saturation magnetization of each sample. This is why we have this decreasing effect as the interactions increase.
Okay, thank you. Thank you very much, Patricia.
No, thank you.
Is there any other question? In the meantime, I have one question, Patricia. Did you consider some dead layer effect in your particle?
Yeah, actually, the surface contribution, we cannot precisely address it to something. So we expect that we have a canted surface as a consequence of the small sizes of the small quartz nanoparticles, or as a canting effect that can be a consequence of breaking of symmetry or coordination with the silicon atoms and other oxygen atoms in the silica shell.
Okay, thanks.
No, thank you.
Any other question from the audience? If not, I would like to thank you, Patricia, again for your presentation. We are